Alright, this is chapter 1.3, example 1. A student takes small steps away from a motion detector at an approximate constant rate. The time in seconds for which the student walks away and the distance in meters the student walks away is recorded in the table. So basically, a student is walking away from a detector at what he feels like is a constant rate. And the time is recorded for how far away the student is in seconds. So at 0 seconds, it's 0.25 away. At 1 second, he's 0.835 away. At 2 seconds, he's 1.5 away. 1.55. So we're going to start off just by finding the differences. So this is a +1, this is a +1, this is a +1, that's not a minus, it's a +1. Okay? And then the bottom part, 0.85 minus 0.25, 0.85 minus 0.25 is 0.6. So we added 0.6. 1.55 minus 0.85 is 0.7, so plus 0.7. 2.2 minus 1.5 is 0.65. So he's not quite as consistent as he thinks. Go figure. 2.75 minus 2.2, so 0.55. So again, he's not quite as consistent as he thinks. So you're right, it's not a perfect linear model, but they're all about the same. So we're going to find the average, just like we did earlier. So the average change in y equals, we're going to do 0.6 plus 0.7 plus 0.65 plus 0.55, and we're going to divide it by 1, 2, 3, 4 items. We're going to divide it by 4 terms. And we get an average change in y to be 0.625. And I'll just leave it at 3 decimal points. It's not like it goes on forever. So, we have our change in y. When we divide it by our change in x, 0.625 divided by 1, still that's our rate of change. So y equals 0.625x. And our starting point was 0.25. So this function right here models this set of data. Okay? If I were you, scroll down to you try it number 1 and see if you can do it. Alright? Alright. It says Tracy, a long distance runner, times herself as she runs a half marathon, which is 13.1 miles. The distance is measured in miles and the time is measured in minutes. Generate a linear function model for the situation. Based on your model, how long to the nearest minute will it take Tracy to run this half marathon? So first things first, generate a linear function. That's what we already kind of know how to do. So again, everything up top is adding 1, adding 1, adding 1, adding 1. On the bottom, that's almost plus 0.8. 16.2 minus 8.5 is 7.7, so she added 7.7. Took her 7.7 minutes to get there. 24.6 minus 16.2 is 8.4. It took her 8.4 minutes to run the second mile. 33.1 minus 24.6 is 8.5 plus 8.5. 41.8 minus 33.1 equals 8.7, so plus 8.7. Alright. To find the average, so the average change in y, so delta y, the average is, 7.7 plus 8.4 plus 8.5 plus 8.7 divided by 4, 7.7 plus 8.4 plus 8.5 plus 8.7, enter 4, and you get 8.325. So the average change in y is 8.325. So y equals 8.325x. And we don't know our starting point. I just realized I may not have done this on the earlier example. And if you caught that, excellent. But we do not have the starting point because we don't have where x is 0. So We could hypothesize that it's at 0, but for this graph, if our rate of change is 8.325, if our rate of change is 8.325, and we're only going back 1, so 8.5 minus 8.325 equals 0.175. 0.175. So here we go. Plus 0.175. I don't know, like I said, I'm going on 3 decimal points on this. I would never go over 3 decimal points for these things unless I tell you otherwise. So that's a function that fits this. And I think the book may only go by 2 decimal points. But then it says, how long will it take her to the nearest minute to run the half marathon? Well, the half marathon is, they tell you, 13.1 miles. So we're going to plug in 13.1 for x. So y equals, what do we say, 8.325? 8.325 times 13.1 plus 0.175. Shove that in your calculator and you get 109.23. So it'll take her 109 minutes, or just shy of 2 hours, to run a half marathon.